Hello everybody. I think we can start. How can you hear me? Everything's fine?
Yeah, it's okay. We can start.
Okay. So we continue yesterday lecture, and there was well, simply looking matrix game that if you have any, by the way, if you have any suggestion or questions about yesterday tasks or something, you can write in Slido, and then later I can read it. So this game, how we can analyze it? Okay, so basically there is one obvious Nash equilibrium, which I can show you by using this best reply correspondence. So if we mark best replies of first player, then we can see that best reply are these numbers. Okay. And if we mark best replies of other player, we can see that here it's there, and here it's 2. Okay, so we have only one profile, which is best reply, and this is a pure Nash equilibrium by definition. And except this, there are also 5 different Nash equilibria in mixed strategies. And if you put this matrix in algorithm in NashPy, you will find that there are in total 6 different equilibria, and this is really not obvious. So if you have a little bigger matrix than 2 by 2 or 2 by 3, then the number of equilibria can increase in great amount. So that's why a big problem are difficult for theoretical solving, especially. So we use some heuristics algorithm to calculate. Okay, so to clarify things, what is mixed strategy? I said that mixed strategy is a probability distribution over the set of pure strategies. So if you have, for example, if you remember our yesterday game, when we play the most distant number, okay, then by dominance, we may conclude that there are 2 possible meaningful strategies, name 1 and name 100. And you can remove any other strategy from consideration. But these 2, if you want to find an equilibrium strategy, you need mix on the set of these 2 strategies, pure strategies. So the equilibrium strategy in this game is to mix, but actually the correct number of mixing are dependent of the number of players, and you can solve this game for 2, 3, 5 players, and you can see that it will be slightly different, not 50-50, but if there are a lot of players, then 50-50 is a very good approximation of equilibrium strategy. So mixed strategy Nash equilibrium is generalization of pure strategy equilibrium. And well, Nash, his theorem is that every finite game has at least one mixed strategy, mixed Nash equilibrium. And I said about the mixed strategy a lot, but I want to give you some notation so you can solve any small game that you will meet with this technique. And consider the game, it's like base games for learning 2 players, and each player has 2 strategies. So it's like the simplest possible game, which is still a game, but you can simplify it no more. You can't have 1 player and you can't have 1 strategy. It's like not a game in some sense. So if you have 2 players and 2 strategies, and we can assign them mixed strategy P and 1 minus P and Q and 1 minus Q. It's a probability to play this particular pure strategy. Then this is not payoffs. This is a probability to meet this outcome. So if you have some payoffs here, the probability to meet this outcome is this, and probability to this outcome is this. So to calculate expected payoffs, you need to take real payoffs and weighted by probability of meeting this outcome. So, for example, consider the coordination game with assurance, where you have 1-1 here payoffs and 2-2 payoffs here, and 0-0 in this situation. So you have two pure Nash strategies here, UL and DR. It's two profiles that are pure strategies. But except this, you have also mixed strategy equilibrium. And mixed strategy equilibrium, how to calculate it? Well, if you, for example, if you suppose that player plays P1 minus P, okay, then let it be. If I already said Q, then let it be Q. Q1 minus Q. So when first player choose up, then with probability Q he will get 1, and with probability 1 minus Q he gets 0. So his expected payoff would be Q of playing strategy up. If he plays strategy down, then he get 2 with probability 1 minus Q, and 0 with probability Q. And the important thing is to understand that if Q is a parameter, we don't know it, and suppose that Q equal to 1, then strategy U gives the payoff of 1, and strategy D gives payoff of 0. So it's better to play U. If Q is equal to 0, then it's better to play D. So if you have inequality, it's always better to play some pure strategy. There is actually quite funny cognitive experiment where you have, for example, you ask some player to try to predict the outcome of dropping the coins, or some random outcome, coin, for example, where you have equal probability, and player try to generate some sequence of heads and tails, and if he matches, he get some money for the match. And then somebody specially tuned probabilities, so you have heads 3 times more frequent than tails, and from the experience, this player suddenly realized that there are more chances to meet H heads than tails. How he can change his strategy and get better payoff? Well, if you ask this question, then many persons answer it that I can say heads, generate heads 3 times more likely than tails, and this gives me better payoff. But it's not the case, because if you know that heads are more frequent than tails, that your best strategy is to say always heads, and you can actually calculate it, so you can see that this is true. So if you know that this is not the equal chances, then you better switch to some pure strategy. And the same is here. If these payoffs are not equal, then it's better to switch to some pure strategy. But if they are equal, then you have a condition for the mixed strategy equilibrium. So if we make equality, then we get that, and since players are symmetrical, then playing Q with probability 2/3 and R with probability 1/3, it gives this is a Nash equilibrium mixed strategy for this game. And the funny thing is that actually you play more frequently the decision which gives you less payoff. And this is a little bit strange, yeah, paradoxical result, I think. So you get better payoff here, but you place more frequently this. This is one of the paradoxes of game theory. Okay, we will try to explain it a little bit more in details. Okay, so it's also a very common example of the game theory. Imagine the penalty kicking, yeah, and this is a simplified game between a player and goalkeeper, and we can present it as a matrix. So the kicker can aim for the left or the right, and we think that if goalkeeper jumped in other directions, that there is no chances that 100% that it will be a goal. So and the goalkeeper can jump to the left and to the right. And for now we can just number that it's if goalkeeper jump to the left and kicker aim to the left, then goalkeeper will take this this ball. Okay, and if not, that it would be goal. Okay, so if you calculate an equilibrium, then we will get that 50%. 50% in equilibrium, you should 50% aim to the left and 50% aim to the right, and goalkeeper must jump with equal probability to the left and with equal probability to the right. And now let's change payoffs a little bit. Suppose that right leg of the kicker is not really good. So when he kick to the right and goalkeeper jump to the left, with 75% he goal, but with 55% he just miss. Miss and there is no goal. So the right leg is worse than left leg. And the question is, how do you think it will change the equilibrium? If you have any suggestion, please. Okay, if you calculate it directly, I will try to simplify things. So, but yeah, it's actually maybe it's useful to calculate. So we have P1 minus P here, and we should equalize 1 minus P from the left with 0.75 P. Okay, and now when it's 3/4, okay, and it's 1 equal to 7 cos P. So P is equal to 4/7, and 1 minus P is equal to 4/3/7, and for player is 3/7 and 4/7. Can calculate it. So the result is also interesting. So right leg is not good, but we start to use it more frequently. Yeah. Before that we kick with equal probabilities to the left and to the right. Yeah. And now our right leg is not good, and we use it more frequently. So So this is also, but yeah, if you think carefully, I think it's understandable, because if you have your right leg is not good, then goalkeeper start to jump to the left more frequently, because he knows that left leg is more dangerous. So, and then you start to kick your left leg less frequently, because to equalize chances. So you start to use your right leg more frequently, even if it's not so good as the left. Okay. So another problem to explain a little bit more mixed strategy is well, actually, it's a very good problem to think about, and the formulation is like this: we have n students in the room, and they all want to ask one stupid question, but they actually afraid to look stupid, so they think maybe someone other will ask this question, so I don't need to be stupid. But if nobody will ask this question, then this question will never be answered. So if we have, for example, two students, we have ask and wait. It's two strategies. So the strategic situation. It's actually very common for other application, but yeah, I will tell after we solve it. And other student also can ask or wait. Yes. And if they both ask, they got a payoff of 6. And if the one wait and other ask, then the one who waits get 10, because he doesn't look stupid. And the other who will ask, he will get 6. And if nobody asks questions, then they got 0. And this is a game. The type of game is called chicken game. And why it's called chicken? Well, it's because of old movie where, you know, there's competition between two some strange guys, and they use a car, and they drive one straight line, one to another, and the one who turn down first is a chicken, and the one who do not is macho, for example. And the trick is that if you both turn down, yeah, turn right or turn left, then you get like zero payoff, and you get like 6. And if you don't turn, then you are macho, so you get 9 to 10. And if you both do not turn, then you are very dead, because you are just crushed. So you have 2 equilibrium here, actually 3 equilibrium here. So if we use our usual, I hope, best correspondence idea, then we have 10 here, 10 here, yeah, and we have 6 here and 6 here, yeah, because 6 is better than 0, and 6 is better than 0, and 10 is better than 6. So we have 2 Nash equilibrium, and they are separated like this. If I know that he will turn, then I need to go straight. If I know that he will go straight, then I better turn. And the same is here. If I know that someone, for example, always asks questions, that I just wait that he will ask questions. But if I know that nobody will ask question, then I better ask. So except the pure Nash equilibrium, here we have also mixed Nash equilibrium. And this is where the things start to be interesting. So my problem for you, if you want to try, it's what is the probability, if you have n student, what is the probability that question will not be asked at all, and how this probability depends on the number of students. Okay, so I will give you a sketch of solution for 2 players, and yeah, and you can try. So for 2 players, if suppose that as a player use mixed strategy, with some probability he asks, and with some probability he waits. Then we need to equalize payoffs. From asking, payoff is always 6, and from waiting, payoff is 10p. So equalizing this, we have the condition of indifference for determine the mixed Nash equilibrium. And I can show you this is as a picture. So we have 10p and we have 6, and the intersection is 3, 5. It's a point where the player is indifferent between two strategies, two pure strategy. And why it's Nash equilibrium? As I said, that's the best reply for the best reply. But what is the best reply for the mixed strategy? Well, best reply for mixed strategy looks like this. If the probability of asking of other player is less than 3, 5, then it's better for me. It's better for me. It's better for me to not to ask. Always ask. Yeah, if p is small enough, then it's better for me always ask. If p is bigger enough, bigger than 3, 5, then it's better for me not to ask. But if p is equal for 3, 5, yeah, 3 fraction 5, then I am indifferent of any possible choice. And this is a property of the equilibrium point, that this pure strategy and this pure strategy gives the same payoff, and any mixing of this strategy also gives the same payoff. If you have like number 3 and number 3, so if you create any mixing of this strategy, yeah, 1 minus alpha, then it's always will be 3. So if you have in equilibrium, all strategy gives the same payoff. So this is this line, and this is why I use the term correspondence, because it's not a function actually. You know, a function it's a mapping where you have only one value for each argument, but this is not function. It's multi-valued function. So this is a sometimes you have like whole set of points as a possible value of this function. And if we draw the same thing is for other player, then we have two correspondence. Yeah, red is for first player and blue is for second player. And as Nash noticed that best reply for best reply is the Nash equilibrium, we have 3 intersections here. This 2 intersection is the Nash equilibrium in pure strategy, and this 1 intersection is Nash equilibrium in mixed strategy. So it's very nice, a nice picture to know about if you need to calculate Nash mixed Nash in 2 players game. Okay, so sorry about that. So if you have more than one student, you can't just draw this correspondence. Even for 3 strategies, it's painful, and for n players, it's really not easy. So, but if you solve this problem for n student, you can write the probability, and it will form this nice nice graph where you have as probability that one student asks the question. It's going to 0 when number of students go into infinity. And but the interesting stuff is that multiplication of this probability is actually go to constant. So it's about 30%. So it's about 40% that the question will never be asked, and about 60% that question will be asked. And this almost, well, doesn't depend on number of students if number of students big enough. Okay. So we already played some games, but I have one more I think last game. And if you want, we can try it. We already played game where we have only one Nash equilibrium. It's a very good game where you have the only Nash equilibrium because actually you play it very well usually. We had a game where we have mixed strategy Nash equilibrium, and you should mix between two strategies at second. Third game was a situation where you have many Nash equilibrium and you need to coordinate to find the one, and it was it was successfully done. You coordinate against number one, and now we try to play a game where equilibrium is very unusual. It's not obvious at all, and as far as I know, it's open problem still. But let's try to play, and then I will explain. I will put the link in Slack as usual. So here we have that list name opposite to the previous game. List named number is the winning number, but if two numbers has the same amount, the smaller wins. And to be in this set, you need name this number. So if you zero named numbers do not play. So if someone named one and someone named one, two players named one, two players named two, and one player named five, then five is winner. Because five is a least named number. But if you have like different numbers named by one, then the smallest one is winner. So think about this game. Think about it. And in I think a couple of minutes, I will explain why it's so interesting. Uh, 24 answers so far. Okay. So 30, 36 answers, and okay, I think I will not close, but yeah, I need to announce the winner. So 36, 37. Actually, very interesting game. Um, okay, so I will close now uh, the form. Yeah, it's amazing. Okay, so what is interesting about this game? I will show you the distribution a little bit later. So the interesting is that if everyone choose one, then even 99 can win. It's usual, but usually people do not choose one always, except so they try to use some small numbers, and there are no obvious equilibrium, and there are no obvious strategy for winning, and the winning numbers are very really heterogeneous. So you can, like, in one game you can have one winning, and in another game 13, and another game 7, and it seems that no connection. The only thing that there's a slight correlation between number of people playing and the number, but it's this game also have very funny heuristic. Number 2 is winning in a really big fraction of games. So number 2 is like some magic number. Why? Well, because nobody maybe choose it, or almost nobody choose it. People choose one, or if they don't choose one, they choose like something bigger. But in our game, actually, the number 2 is the winner. So this is really interesting. So we have, you see, we have this distribution. Five players named one player named two, two players named three, three players named four, two players named six, two players named seven, three players named nine. Also very interesting, 2, 3, 4, 6, 7, 9. So 8 and 5, it's not. Then in 11, 12, 13, and so on. And then we have also 299 numbers. So this is quite interesting. And the point is that if you have a game with obvious or simple Nash equilibrium, then people usually understand very good the game. And if the game is not obvious and complicated, then you can't, like, you can't use your intuitive understanding to understand how to play this game. Actually, there are very nice TED talk about neuroscience and game theory by Colin Kammerer, and he made experiments with chimpanzee about finding the Nash equilibrium, and he concludes that chimpanzees are much better than humans in calculating. Well, they play some games, but these games was about Nash equilibrium. So especially when banana was on stake, so chimpanzees are very good in finding Nash equilibrium. Okay, so I hope you saw this blonde scene and understand. So if you didn't, I will give you a short brief. they, John Nash and friends, are sitting in the bar, and they came blonde, very beautiful blonde girl with her friends, and they are not as effective as attractive as this blonde girls. And the friends of Nash, they try to plan how to approach to the blonde girl, and Nash proposed a solution which well, by editor and scenario makers of this film should like should show how he get to the idea of Nash equilibrium. But in fact, he proposed to approach to the friends of the blonde girl, but not her. So, but not to her. And he concluded this is an equilibrium because it's best for everybody. But this is not equilibrium because actually one of the players has an incentive to deviate and get better payoff. But maybe it's also depend of how you define the game. So, but most games theoretical specialists in their blogs, as I read 3 or 4, they have opinions that this is not necessary. Okay, so now we go to the next big chapter, and this chapter is a game in extensive form. So game is in extensive form is a game where we add some time and moves. So sequential moves like chess, it's a game in extensive form. And game in extensive form is basically a tree. You have initial point, it's always 1 point. Then you have vertices that are decision-making points, and ages is possible actions, and each vertex is connected with some player. So he has action to choose, and how this tree is performing. So let's consider an example because it's like funny example, and also I will ask you a question. How do you think? What do you think about this game? So please pay attention. So we have 3 neighbors, and these neighbors want to raise money for small decoration near their house. And for simplicity, we assume right now maybe it's artificial setup, but let's consider it that every one of these 3 neighbors has 2 strategies: give money or do not give money. And the order of decision making is specified before. First, make decision A, so he goes, from the work and put some money in the box, and then comes B after that, and he can observe the decision of A and add some money or not, and then C comes last, and he can also observe the choice of A and B and add money or not. So this is a set of players and set of their strategies. Now, what are possible outcomes? Well, if nobody give money, it's actually, well, no decoration will be made. Exactly 1 give money, decoration is base is small. Exactly 2 give money, then decoration is fine. And if all 3 give money, it's a little bit too much for this decoration. So suppose that we define the payoffs of players like this. If only me give money, only my money are given, then it's the worst possible choice. So I get -1 if I pay and nobody else pays. If at least 1 person give money but not me or nobody, then it's 0. 1 if me and other player give money, and 2 if all 3 of us give money, and 3 is the best choice for every for player. They are a little bit egoistic here, and 3 is all except me give money. So 2 other players give money, I didn't. Base is fine, and this is the best possible outcome. It's the best possible payoff for this for this player. So then we build this tree. So we have A, and he can yes or no. Then we have B, and B knows the decision of A. So B has two decision nodes here and here. Okay. Is a decision node from for A, and this is only one. Okay. Yeah. So we have first decision node is for A. B has two decision nodes, 2, 1, and 2, 2. And C has actually 4 decision nodes, 3, 1, 3, 2, 3, 3, and 3, 4. And now we should talk about strategies. So I said that strategy in game theory is not the same as a strategy in our everyday life. So A has two strategies. So actually we have actions. It's what what players can do in some decision node. And strategy is actions multiplied by information. We can imagine this construction. So if player one here, he knows nothing about other players. He has two possibilities, and this is his strategy. So he can make yes or no. So player A has two possible strategies. Now, player B can be in one node or second node, and he can have two strategies here and two strategies here. So he has actually 4 strategies. What is 4 strategy? It's a yes, yes. We can denote with yes, no, no, yes, and no, no. What's the meaning of this strategy? Well, yes, yes means that I give money if A give money, and I give money if A do not give money. So I always give money. It's two actions for 2 no's. And here it's I give money if A give money, and I do not give money if A do not give money. So it's yes, no, and so on. So for B we have 4 strategy, and for C we have 8 strategies. So C has 8 strategies. And I remember, I remind you the definition that strategy is a full plan of action in future game. So before the game starts, players must define a full plan of action. So here, A has 2 strategies, B has 4 strategies, and C has 8 strategies. So now my question is that right now, game already defined. We have players, we have the action strategies, and we have the payoffs. So now the equilibrium is already here in this game, but to calculate it, we need to think a little bit about. So my question is, how do you think this game will end? So what is the possible outcome? Who will give money, who will not give money, and how many people actually give money for this decoration? If we provided that we take this payoff as rules of the game, of course it can be a little bit not realistic, but so if you have any answers for this, please write. I will see this. I will see your answers in Slack or in YouTube. Everyone are listening in record. Okay, so no suggestions. To solve this game, I mean to solve game in extensive form, it is special. Well, I suppose you've heard about dynamic programming and the principle of Bellman, optimality of Bellman, and here we have reduction, simplification of this principle to the to this simple situation. So here, and in game theory, it's called backward induction. So to solve any game with full information, where all player has information about previous moves, if for example C knows full information about previous moves, then we need to start from the end. So we consider player C, and we look only on his payoffs. Here we have 3 and 2, and 3 is bigger than 2. So in this particular situation, C will choose no rather than yes, because 3 is bigger than 2. Yeah, I didn't say that this is payoffs usually in ordered as players came to the game. So it's A payoff, this is a B, and this is a C. Okay. So 3 is bigger than 2, 1 is bigger than 0, yeah, and 1 is bigger than 0, and 0 is bigger than -1. So this is choices of rational player C, and we can remove, after this, we can remove C from the game, just putting these payoffs here. So since we know that C is rational and C will choose what is best for him, so we just can remove it from his remove C from the system, from the model. Now we have decision of B. So we have 3 here and 1 here, and 1 is bigger than 0, and 3 is bigger than 1. So we can remove B. And now we have A, and we have 1 here and 3 here. So full our result is, it's also called Nash equilibrium, I will explain, is this. A didn't give money, B give money, and C give money. So this is a Nash equilibrium for this game in extensive form. And well, why it's Nash equilibrium? Well, because if C deviate for any decision, for example, here, C will can't increase his payoffs. If B deviate separately, then B cannot increase his payoff, and A, the same is for A. Okay, so this is equilibrium called subgame perfect Nash equilibrium. Why it's subgame perfect? Because this is an equilibrium also in every subgame. What is subgame here? Well, subgame is any subtree. Here, for example, this is subtree, and this is also subtree. And the equilibrium that we have found, this equilibrium is also an equilibrium in every possible subgame. So that's why it is called subgame perfect equilibrium. So the interesting paradox: the decisions that we make are determined by consequences of actions that never happens. And in extensive game theory, it's especially interesting because player make decision based on the possible actions that other players can make, but this player never actually do this stuff because they never happen to be in this situation. To clarify a little bit this idea, I will show you another problem, but yeah, I will not solve it. I just give it you as an idea. Well, this is quite popular for some interview, so you can maybe think about it. So we have a greedy bandits. Actually it's a puzzle. If you like puzzles, you can solve it. Every evening in cave gather 1,000 of bandits, and they are ordered by age. So every day they vote for the same proposition. Is it time to divide all the loot they gather equally and run out? If more than half vote yes, then game is over. Everyone got equal share. If less than half vote yes, then bandits kill the youngest bandit and get the next day. So this game will surely end before the last bandit will die. Because every day it's or finished or the number of bandits is reduced by 1. So yeah. So every bandit firstly wants to live and secondly share as big as possible. And this game is also can be solved by using games in extensive form. But okay. Okay. Now I want also consider some example that illustrates how how game theory is different of our intuitive thinking about some strategic situation. And this is not easy example, so I need some yeah, we have some questions. So sorry, I get back to the problem. Okay. So if more than half vote yes, then game is over, and half is not more than half. So if yeah, it's actually my miss, no less. So otherwise, bandits kills the youngest. So yeah, right question. So if more than half yes, then game is over. They got equal share. If not more than half vote yes, then bandit kills the youngest. So yeah, I hope I answered this question. Okay, back to the illustrative example. So we have a show, and this is a strategic show, and we have 2 players, and they need to split. They need to split $500. Okay. And they can choose A or B. It's their cards that they secretly put in some box, and then the box open, and they see this the decision. And if they both choose A, then the division is that first player gets 400 and second player gets 100. And if they both get choose B, then first player get 100 and second player get 400. And if they discoordinate, then they get nothing. Yeah, and this is a funny game. If you really play for money, then it's very interesting how to what is the best strategy. Actually, we have 2 Nash equilibrium here. 3 actually. We have 2 in pure strategy. I think it's quite easy to see that this both are Nash equilibria. Yes, and there is one in mixed strategies where you make with some probability, and to fulfill it, I just use Nash pi to put this game and to calculate it, and you see the three Nash equilibriums that algorithm actually found is 1 0 1 0. Both players play A. 0 1 0 1 is both player plays B, and 0.8 0.2. So first player with 80% probability plays A, and with 20% probability play B, and the second player is makes the opposite. So you play 50% choice, which gives you the most amount of money, and you can calculate expected payoff for each for this case. But now suppose that first player have possibility to burn $200 before the game if he wants. So this strange condition, but can it change the game? Can it change the game? Well, from our intuitive point of view, how it can change the game? If he burned $200, it's his problem, and nothing can change the fact that when you put card in the box, then well, how the past can affect this. But for this situation, I just draw the matrix. So suppose first player burns this $200. So now payoffs are like this. Here he gets, instead of 400, he gets 200, and here he gets like minus 100, minus 200. So we just reduce his payoffs for 200. But from game theory point of view, you can't consider this game separately. You need to consider it as one game. So first player can I just draw the tree, so can burn, yeah, or not, burn or not, and if he burn, then he choose A or B, and here he can choose A or B, A or B. And here second player who doesn't know this choice, and this is a game with incomplete information. So this player do not know what first player did on this step, but he knows that this money were burned or not. And second player also choose A or B, and then they get the result. So we have game of this form. It's a little bit A and B here. Yes, sorry for A, B. And I will not draw the full payoffs because they are in matrix on previous slides. But how many strategies now has each player? Well, first player has 1, 2 information nodes. So he has 1, 2, 3 information nodes, and 2 possibilities for each. So it's in total 8 possible strategies. So first player can burn A. Well, the funny thing is that if you burn money, you will never be on this node. But to specify the strategy, you need to specify your action in all possible nodes, not only nodes where you will be for sure. So this is a little bit strange thing. So player A has 8 strategies, and player B has actually these nodes are connected. So player 2 has 2 strategies, two nodes, and 2 possible strategies for each node. So it's 4 strategies. So player 2 has 4 strategies, and player 1 has 8 strategies. Now we can put it into matrix, and matrix would be rather big. So what we did, we transform game representation of a tree representation of this game into matrix form. You always can do this. So, but not the opposite. So if you have only equivalence in one direction. So every game in extensive form can be transformed in matrix form, but not back, because we lost some information about the game structure in this process. So we have 8 strategies: burn money AA, burn money AB, burn money BA, burn money BB, and so on, and not burn. And we have 4 strategies for second player. And the interesting stuff that when you start to analyze this matrix, you will find that some strategies are actually dominated, and you can remove them. So dominated strategy are strategies that gives less or equal payoff than other strategies, so rational player will not play it. So if you start to remove dominated strategies, you start to reduce this matrix, and you will finish with these 2 possible strategies, where player 1 not burn money and play A, yeah, because the first letter is irrelevant because it's for burning money. So he plays A, and the second player also plays A, and they have split for 100-100. And from the game theory point of view, it's the only solution now. So no other equilibria exists here. And this is actually surprising, because when you have possibility of burning money, you never maybe think that it can change the whole game and change the equilibrium for this game. Okay. So when you have complex structure or complex rules of games, it's very important to understand how these rules will affect the strategic outcome. There was a very famous example from game theory lectures of Tim Rowegarten. He has a lecture series about algorithmic game theory. It's on YouTube. I think you can find it. So in first lecture, he tells about one prominent example. So about fail of mechanism design. I mean, in this situation, fail in construction game theory, game theoretic construction. So it was Olympiad, Summer Olympiad in London in 2012. Yeah, and it was women badminton championship, team women championship, and they for some reason they do not when they create scheduler for the games, they do not put the games at the same time, because they want to show it to the maximum amount of people, for example. I know. So they put the last game in group, in sections, one after another. And the problem is that situation in groups was very strange. So we have like 2 teams. I think it was China and Korea teams, and they need to lose to get better match in next round. Well, because if China here wins in this situation, they will face their another team, so they reduce the chances to win a medal. And if Korea lose in this win in this game, they will face the strongest team in the tournament, from another China team, and they do not want to do this. So they both wanted to lose, and if you know how badminton looks, it was really pathetic match, because when two teams try to lose in badminton, it's really bad. So you can find it on YouTube. But the problem is that the rules were constructed badly. So the best possible strategy for players was to intentionally lose this match. And there are some sport where you can do it quite naturally, but not badminton. So it was a huge scandal, and they were disqualified two teams. But is it really the players who you need to blame if the rules were created like not good? So we must to construct equilibrium, to understand the complex structure of rules, we need to understand players and their preferences. So even simple games can be quite difficult, especially if you came to some auctions and public goods allocation. So when we have game, sometimes you can change the game to your favor if you know how to propose some new strategic moves. So, for example, you have game and you want some behavior, but you can't explicitly ask players to do what you want, but you can propose some intermediate move or change a game structure a little bit. Well, this is example from a very nice book, Games in Action, by, I think, Gintis. So we have situation. We have here a guy, and this guy actually scrap a little bit a car of other guy. So this guy wants to repair, and they do not want to ask some insurance company. They want to settle it like between them. Okay, so this guy Tony, he has two options. Can demand, because he has strong suspicions that if he give money for this, because car is not very new, so if he just give money, then no repair will be made, and this guy just put this money in the pocket, so he just lose $80. If he demand the check, then if this guy do not repair, then they both got zero. But if he repairs, then Tony will lose his $80, and this guy will get satisfaction estimate around $20. But it's not money; he just polish car from one side. But car is not new, so it's not big deal. So it's not possible to right now. If we solve this game by using backward induction, we will have the situation that it's better to repair than do not repair for this guy, and minus 20. And for the Tony, it's indifference between this option. He can give money or he can demand check. Otherwise, he lose $80. Okay. So they propose intermediate move. They propose the idea that Tony can give half of the sum before and the rest after the check. And in this situation now, Vic has incentive do not repair and get 40, and it's better than get repair with a moral compensation of the estimation of $20. So in this situation now, the equilibrium is changing, and now it's better for Tony because 40 is lose 40 is better than lose 80. So this is an example how we can change the game by proposing intermediate moves. Okay? And actually, if you have a strategic situation in an extensive form and other form, all possible game changing is classified on 3 possible situations. So you have 3 possible strategic moves, threats, promises, and commitments. So it's 3 possible situations, 3 possible action you can take to change the game. What is a threat? What's commitment? Commitment is that in future, in some point of the game, I will do some action A, and this will be in any case irrelevant to your previous moves, and nothing can change it. So commitment is I will do this, and I don't care what you think about it. Promise as it's if you do something for me, good, then I will do B, something for you. And B is something good that you generally do not want to do. And threat is if you do not do A, then I will do if you do not do A, then I will do B. B is something bad for you, something that I usually do not want to do. So I say you do A. If you do not do this that I want, then I will do B. Well, let's consider this as a simple example. We have a child, and this child don't want to eat broccoli. So parents try to ask him to eat broccoli, and if child eat broccoli, then child get -1 payoff, and parents get 1 payoff. Yeah, payoff, because they put some healthy food in the child. And if child refuses, then child will get 1 because he don't want to eat broccoli, and parents get -1 because it's bad for child. So what is the promise in this situation? Well, promise is if you eat broccoli, we will give you candy. So this is a promise. And if child refuses that, nobody will, no candy will be for child. But if he eat broccoli, then parents have a decision, give candy or do not give candy. Of course, it's bad for maybe for moral conditions, but they do not want to give candy. It gives them less payoff. So they have like incentive to deviate at the end. So they need to, yeah, but this is how promise works. If promise is working, then you need to pay something to keep this promise. If what is the threat here? Threat is if you refuse to eat broccoli, then we punish you. So if threat is working, then you do not need to pay anything. It's bad about threat that if a threat is credible, if the child believes that that threat is real, then it's cost you nothing. But if child still refuses to eat broccoli, then parents have a dilemma: punish or do not punish. And they don't want punish actually, because punish is bad for, yeah. So when threat is not working, then you need to pay to make it reality. And commitment here can be like parents make a commitment to eat broccoli every day in any situation. If child eat broccoli or refuse broccoli, but parents eat broccoli every day, and this is a commitment. And maybe it can change in some situation. It can change the strategic outcome. So to create credible commitment, threat, or promise, you need to do something that you do not want to do when time comes. This is a principle. If you have a promise that you actually want to do, then this is called assurance. It's not a promise, it's assurance. And the threat that you do not want to implement is called warning. So, and this strategic move actually can change. It's in game theory. It's called how it called how it is called. Not trash talking, but it's like empty threats. It's oh, I just forgot the term. Sorry. Okay. I think that, okay, how to make your move credible? Well, there are some interesting ideas from game theory, from negotiations, how you can make your move credible. Well, you can make your position less flexible, for example. And this is maybe paradoxical outcome. So if you have negotiation about, for example, your salary or some decisions in real life, then when you make your position less flexible, then this gives your additional points in bargaining, in negotiation. What is the example? Well, for example, you have judgment day machines, devices, or judgment day devices. If you don't know that in the Soviet Union, there was special devices that measure the radio waves on big cities, and if there are no activity for a long time, they must launch the last rocket in America with nuclear bomb. So, and the idea of this device is that you can't stop it. So even if everything destroyed and all cities are razed down, for example, with nuclear bombardment, this device doesn't depend on any politicians or president or secretary or someone. This device is absolutely automatic, and knowing this, it makes invasion or first attack like less likely, because it's not. What's the point of bombarding if you just activate this automatic device? Okay. There is a very nice old British series, Prime Minister, and one series about nuclear dilemma, and this, about salami tactics. And I will, I think I can find it in mobile, and I will send you this explanation about how this works. So it's called salami tactics. Salami tactics is slice by slice, where you can, if you don't have credibility, you can be squeezed by one. You have one small step, and this step is small enough to make some serious reactions. So you just like swallow it, and then another small step, another small step, another small step, and then suddenly you just lose. Okay, so well, example of how you can increase your credibility by reducing your liberty is a chicken. Well, chicken in first setup, as I said, it's two cars, and they are going to some straight line, and who turn is a chicken, and who goes straight is a macho. For example, you can old movie from my childhood, Cry Baby, with Johnny Depp, and this is a final scene is like an example of this chicken idea. So what is the best way how you can play in chicken? Well, you can speed up your car, and then you just remove your wheel, running wheel, and you just throw it into the window. So you remove your ability to turn, and after that another player just will turn, because he knows that you just can't physically turn left or turn right. So this is like a radical way to win in chicken game. Okay, so I think it's a good time to make stop, and I can answer some questions, and I think we can continue after the break. Okay, so I will try to explain the questions. The only thing that I need to remember, the reference of this question. So can you maybe edit your question? Can you explain better why is this a Nash equilibrium? To what about what problem are you asking about? So I can understand. Examples where game theory is used in real life besides the games. Well, actually, it was in first lecture. I can talk about application a lot. Well, the different areas, but well, I think that the most profitable application is constructing of new auctions. So if you have auction, it's the rules of the game, how bidders, players should how they, well, at what conditions they will win some prize of auction. And if you have an efficient auction, it make properties to example, 100 years ago approximately, there was a special auctions about selling the oil fields. So if someone like drilled, found oil field, and they do not know the price of this oil, so they just create a sealed bid first price auction, where every company puts some price on the envelope, and then they open all envelopes, and the guy who proposed the highest price, he was the winner of the oil field. And then after some time they realized that the winners became a bankrupt after they win this oil field, because if you have an auction with a sealed bid first price, then the loser who estimate with mistake, well, I think I just wrote because it's a little bit difficult for me. So let's consider a situation where you have some good, for example, oil field, and this is a real price. And there are different players, companies, and they do not know this real price, but they try to estimate it. And usually people are quite good in estimation, but they also have some bias errors. And we can assume that these errors would be distributed something like this, like normal distribution around the real value, not price, real value. Okay, real value. So if you have first price sealed bid auction, then the guy who make the worst possible bias to the higher price, to the higher value, would be the winner. So they systematically will solve this oil field to the guy who doesn't know this value, who overestimated, and they just became bankrupt. So that's why, for example, for Google auction, you have a second price auction, because second price have a very nice property. If you have second price auction, you can bid your real value, your estimation of real value, and you pay the second price. So and this is an equilibrium strategy. So in first price sealed bid auction, the equilibrium strategy is to name half of your estimation value. It's the best you can do. But if someone, for example, stupid enough, he will pay full price, then he will become bankrupt. But in the second price auction, you you have incentive to put efforts to understand the real value, and that's why Google is so successful in sponsored search auctions, because it stimulates people to get better and do not lose money. Yeah, of course, I publish slides after the lecture. Yes. I think yeah. In the example where we have two Nash equilibrium, what is the preferred strategy? Well, this is a problem with you mean real game where we played with numbers, probably. Well, the problem with Nash equilibrium is, well, as I stated, the best side of, or the best idea of Nash equilibrium is that it is always existed, at least in mixed strategies. So you can, in unknown game, you can launch some algorithm to found it, and you will get meaningful result, because you will look for something that you know actually exists. If you but if you have many Nash equilibrium, some of them can be efficient and some of them can be inefficient, and you have no way to understand what Nash equilibrium is better, what Nash equilibrium is worse. I mean, before. So you need to find particular game and understand how to change the outcome, how maybe to change the game, so you can understand what Nash equilibrium will be better for people. So there's no such thing as a preferred strategy, because every Nash equilibrium is a possible outcome for rational players. Even if some equilibrium are better, the payoffs in some equilibrium are better than in other equilibrium, doesn't matter that people should choose this one instead of that one. Because for rational player, every equilibrium is a rational choice. Okay, if you have another questions, okay, so we have a break till 1 p.m. Yes.
Yes.
Okay. Okay, so I think we can continue. And okay, let's wait a couple of minutes. So again,
You can continue.
okay. So now sorry. I want to make some small add-on for behavioral game theory. Well, behavioral game theory is like a little bit out of topic because behavioral game theory is essentially how a game theory model fails in in human society. I mean, so when a model predicts one outcome based off some axioms of rational choice and assumptions about rationality and assumption about intellectual properties of agents and so on. So when we have some prediction of the equilibrium, and when we create a model of an experiment based on this model, and we try to we propose it for real human people to make decisions, and they basically fail. So they do not the things that are predicted, and this is actually a force to think about what we miss in our model, what we didn't include. And I want to tell you about two models, just to show you how real people how they differ from the modeling and algorithms. So it is famous ultimatum game, and it's very simple, actually surprisingly simple. We have two players, and one player can propose a split of 100, usually $100. And for example, he can propose 50-50 split, or he can propose 30-70, and so on. So he can propose some split. And then go to another player, and this player can either accept or reject this proposition. If he rejects proposition, then nobody gets nothing. If he accepts, then he get what the proposed split of first player. So seems that the players are in equal positions. Yeah, first player can propose but can't accept, can't force to accept other player, and second player can change the split of proposition can only accept or reject. And game theory actually propose that if someone propose you split $1 for you and $99 for self, then you should accept, because $1 is better than nothing. But in reality, it never happens. Almost never happens. So we have this results. It's from experiments in many different countries. It's an average results, and we have here that 66% of propositions were around 41-50% split. And if the proposal part of the second player was less than 30%, then rejection rate rise to 85%. So there was probably one or two deals where the proposition was less than $10 and they actually agree, but 85% of them just refuse. And what is interesting is that when they tried some different tribes. I mean, tribes that live in from ages from some time. These tribes, they actually showed behavior that is suitable for model of game theory, and it was very surprising because some tribe like Indonesia whale hunters, La Malera, they actually propose more than half, and they refuse in like 30% when they were proposed more than half. It was very unexpected behavior, but some tribes actually propose less than 10% and always accepts, like Peru in Peru. So it's quite different, and this ultimatum is used for cultural, for measure cultural differences between different nations, people. For example, in Europe, in America, these numbers are almost the same. In Japan, they propose 10% less in average than in Europe, and in Israel, they proposed 10% less than in Japan. And it's like the natural well, it's like a national habits. So if the amount of sum is rising, so except instead of 100 it's like 1000, then two effects come to play. First, the number of equally split propositions rises, and the rejection of small share proposition reduced. So it's also quite interesting. But what is interesting is that many persons, they propose 50-50, and the researchers, they maybe start to think that maybe we can try something different, and they propose the game Dictator, and Dictator is the game where second player doesn't have possibility to reject. So it's like a strange game. First player just propose a split solution, and second player just do anything, do nothing. But even in this situation, 30% of players, they propose 50-50 split. So it's quite unusual. Yeah, and interesting. There's there is modification of Dictator game called Anonymous Dictator, where you can see the guy who make split. So they try to like reduce incentive of so maybe people want to take everything to themselves, but they're afraid that they would be known for this, so they put some special wall between them. And in Anonymous Dictator, people actually take for themselves, but 5% of people, even in Anonymous Dictator, they propose split 50-50. It's like experimental percentage of altruism in the game. And you see, when you have no identification, then the number of taking everything to themselves is high. But if there is identification, there is a spike at 50-50 split. And it's interesting that in different societies, dictator distribution is different. I mean, here is the propositions, how you propose. So in Western, actually Western society is more competitive. So here people take everything to themselves. But in developing and primitive societies, it's a spikes on 50-50 deals. So this is quite interesting. Also, very nice and interesting book, Honest Truth About Dishonesty by Dan Ariely. I already told about this author, and his field is research about irrationality, how people behave in different situations, how they cheat with rules and so on. And he made some experiments, very interesting experiments. And I will tell you about one of them. There was a candy machine in there, I believe it was in Stanford or something. And there was a special regime where you can put this candy machine to the gaming mode. So you can, like, you pay, you can obtain candy which is worth $1 for 70 cents with probability 0.7, for example. Or you can, so you can, and you pay $1 and with probability 0.7 you have candy for which is cost 70 cents, and you have 30% chance to get candy and $1. So you have 30% chance to get candy for free. And this gamification is actually rise the profit of this machine 3 times. But then they put the price for the 0. So in new regime, machine working like this: you put $1 and you always get $1 and candy. So it's like candy for free. But all signs were left that cost is actually 70 cents. And there was a phone number of service with indications that if a machine is broken, please call. And there was special investigations that watch how people behave. But usually it was like this: person came to machine, drop coin, get candy, then drop another coin, get another candy, then drop another coin, and get another coin. And then they suddenly realize that there's something wrong with the machine. But well, nobody actually calls by the service number. And if they saw the friends around, they go there to the friends and give them candy as a present. And it was like some self-justification of the unfair candy getting behavior. And yeah, it was rather interesting how people behave in such strange situation. And he has also different experiments about cheating and about how people behave irrationally. So now I want to tell you about repeated games, because as I saw you yesterday, you have lecture on multi-agent reinforcement learning, and you had repeated games here in equilibrium and so on. But I want to tell you about like a source idea of repeated games and how they rise in the game theory field, and then this idea go to other fields like algorithmic reinforcement learning. So when we have game, repeated game has special properties. And one of the properties came from the multiplication of strategy spaces. When you have like repeated game, it's a game in extensive form, but you play the same matrix on each step. So you have like a simplified version of this. So let's imagine this game. Yeah. Let's analyze it for one round setup. So we have best response for first player here, here, and here, and you have best response for second player here and here. I just remind you that when we consider best response for first player, for each row, we compare these two numbers as payoffs of player for his strategies if strategy of other player is fixed. And if we consider the best response for second player, then we fix the row, and then we compare the numbers in this column. Yeah, for one row in different columns. Okay, so Nash equilibrium is here. Is the only unique Nash equilibrium here is DM, and actually it's really not efficient because first player can have 2 is less than 4 but bigger than 1, and 1 is less than 3 and 4. So it's really bad for second player to have this Nash equilibrium, because his payoff is like very small. Yeah, so imagine that we have 2 rounds of this game. Then first player can get maximum in equilibrium 4, yeah, or he can get 8 here, for example, or he can get one. So we have possibilities. If we have 2 rounds, we can have a sum of different numbers, but at maximum we can get like this number. And this is the best possible profile which is not in equilibrium. Why it's not in equilibrium? Because second player has incentive to deviate and get 4 instead of 3. But if they found some way to keep this UL technique, UL profile, then they can get bigger payoff. And but the problem is that if you have a finite game, it's really not easy to, because if you have final game, you have last round, and in last round you have incentive to deviate because it's last round, you don't have further game. So in second round, in last round, second player thinks, okay, it's last round, so no retaliation, so I can deviate here for 4, and I can get better payoff. And knowing this, in last round, first player has intention to deviate here, for example, to punish this guy, and so on. So, but if you have uncertainty, yeah. So if you have uncertainty with this game, for example, we can imagine a game where you have probability to go to next round, and this probability is, for example, delta. Yeah, delta from 0 to 1. If you have probability to go to round number 2, then it changes the game a bit. You can consider the strategy of both players. Play UL if nobody deviates. If someone deviates, we will change to DM here. And this idea of we will play not equilibrium in each separate step game, but if someone will deviate, we will punish him. This idea happens to be an equilibrium in bigger multi-step repeated game. And to see this, I will go to prisoner dilemma. It's like classical setup with numbers. So we have two players, and they can cooperate or deflect. And if they cooperate, they get 3 balls. It's not years in prison, it's points. So they want to maximize their points. If someone deflects, then he gets 5, this gets 0. And if they both deflect, they get 1. Okay. So first start to solve this repeated game for any finite repetition. As I said, if you have finite repetition, then we have rounds. For example, we have round 1, we have round 2, we have round 3, and so on. And we have round n. And at round n, since this is the last round, it's quite natural for each player to try to cheat and get better payoff. So they know that on the last round they will play D. But then we can eliminate last round and understand that this is a last round with uncertainty what to play. So, but we will play D on the last round. So on the n-1 round, we also will play D. And continuing, we can understand that playing DD, deflect on each step is a subgame perfect Nash equilibrium. But it's not the only equilibrium in this game. So hopefully we can find something else. But to do this, we need to calculate expected payoff for the game. So imagine that we have this game with probability of going to the next round, or we can tell it also discount. Well, discount, the idea of discount is that payoff of 3 today is not the same as the payoff of 3 tomorrow. So you need to, well, if you get 3 in this round, in next round it would be delta 3 right now, the value, and in next round it would be delta square 3, and so on. And it's actually a very usual way to define the payoff for example, for multi-agent problem also. So you need to calculate expected. Well, if you are familiar with the reinforcement learning algorithm, you know that this is the very usual way to define the value function for the strategy. Okay, so how to? Well, I hope you know that this is equal to 3 divided on 1 minus delta. Geometric progression, school formula. Okay, so knowing this, we need to understand what will happen if we play strategy, and for example, if we always cooperate. If we always cooperate, the payoff of both players would be 3 divided on 1 minus delta. And if we always deflect, we will get 1 plus delta squared. It would be 1 divided on 1 minus delta. So now we will try to consider special strategy, which is called green trigger. Green trigger, it's a strategy that cooperates, always cooperates until other player deflect. And if this has happened here, for example, then he starts to deflect always, doesn't matter what, to the end. So it's basically, we have 2 states, and we have one transition from one state to other, and no coming back. So this is green trigger strategy. And to understand that this is an equilibrium strategy, we need to calculate their payoff for possible deviation. So if we use green trigger strategy, and if someone deflect, is it profitable to keep deflecting for him? And if no one deflect, is it profitable to deflect at some point for other player or for me? So we know this matrix. Now, if we always cooperate, yeah, then let's calculate what will get other player if he will deflect. Well, if he will deflect, he will get 5 on first step, and then he will get always 1 in every future game, because we use green trigger strategy. Okay, and and if you do not deflect and cooperate always, we also do not deflect, so we get 3 and every time. So the expected payoff from infinite repeated game with delta discount is equal to 3 divided on 1 minus delta. And if first player deviates, and it is, I think it's clear, must be clear for you, that the best possible payoff is when he deviates at first step, because then his payoff will not be discounted later. So it's the best possible payoff he can get. It's deviating at first step, and he gets 5, and then he gets delta divided on 1 minus delta. So it's a future profits of playing always deflect discounted on delta because it would be in next round. So now we should compare these two, and we want that this expected payoff of deviating will be always less than not deviating. Okay, so we have the condition for delta. So if delta is bigger than 3 divided by 4, yeah, 3, 4, then there is no profitable deviation at all. So if the discount is big enough, or we can interpret it as a probability to go to next round, if it's big enough, then it's better for us to cooperate. And this is very good because Prisoner Dilemma was like a very strange game, and it was strange because in real games people usually cooperate, but in theory they should deflect. So now we have situation that if we add uncertainty to the game or repeated game repetition, then for some condition it is rational to cooperate. So cooperation arises when people start to think about future uncertainty. And what is interesting, and this is like property about, that what is the difference between theory and practice, that in theory and practice is the same, but in practice they are not. So what's strange thing that for every finite game, arbitrarily big enough, it's not working. I mean, this reasoning, but for infinite game, it is working. So it is working, and cooperation is actually profitable if delta is large enough. But tit for tat is green trigger is very severe strategy. One wrong step and no comeback. So no returning back. And in real experiments, real people, they usually do not use green trigger. They use as another strategy, which is called tit for tat. Tit for tat is when you, for example, if someone deflects you, you deflect him, and then you return to cooperation. Maybe after 1 or 2 steps of deflection, but then you return to cooperation. And this brings the idea that maybe tit for tat is better. And so what is tit for tat? Basically, when you play Prisoner's Dilemma, if, for example, your opponent play C, D, D, C, 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 D, C, for example, such sequence of moves, then what is tit for tat strategy doing? Well, tit for tat, at first step, always play cooperate, and then it mimic previous move of opponents. Extremely simple strategy. So it's cooperate here, it's deflect here, it's deflect here, it's cooperate here, and so on. Cooperate, cooperate, deflect. So it's like if you deflect me, I will have my revenge for 1 round, and then if you return back to cooperation, I also return back to cooperation. And why is tit for tat became so famous? The strange thing is that tit for tat is actually not an equilibrium strategy. It's not equilibrium it's not subgame perfect Nash equilibrium, but it's weak equilibrium in some sense. So in 1980s, Robert Axelrod, also very prominent computer science specialist and game theory also, he invited researchers to participate in very unusual competition. It was 200 rounds round-robin tournament of computer programs. And they play Prisoner Dilemma with each other in a tournament. And the scorer was the sum of points and they use the same numbers that we already saw on this matrix. 3, 3, 5, 0, 1, 1. And surprisingly, on first tournament, it was like 20 or so different programs, and some strategies were really complicated with some Bayesian formulas and gathering some data about others. But the winner was tit for tat, the simplest, almost the simplest possible program. And if you want to replicate it or try your own tournament, it's very simple. You can use Python package Xherod, and this package have a lots of strategies implemented, and you can create different setups and matches between different strategies, and you can analyze and visualize result quite beautifully using all power of Python. And to do this, for example, you need just import Xherod package. You can define players and then start match or tournament, and then just show the result. So, for example, for this code, it will be first it will be match between cooperator and alternator. So alternator is doing the opposite, I think, to the what cooperator doing. So here we have that alternator is very good against cooperator, because cooperator always cooperates, and the cooperator and cooperator, they agree, they have 3, and cooperator against alternator has very small 1 score, and alternator against alternator is like so-so. So and when we have a tournament of many programs, I replicate here the original excellent tournament, but in this tournament, tit for tat actually not very good. I don't know why. So tit for tat is here, and this is the score with the distribution for different strategies. And this actually this set of strategies are called nice. Nice is the type of strategy. It's tend to cooperate if possible. So why the tit for tat is so good here? Well, because it's very its first element was very effective, because it get many points against nice programs, and not very bad against bad programs. And if we want to see this table, you see this is a nice strategies with a green square, the strategies that cooperate between each other, and here a lot of strategies that try to fight with each other. And now we have implementation on neural network here, and right now neural network are the best possible players in this tournament as far as I tested. Yeah, so if you want, you can add your own strategy and try to participate in these tournaments. So now I will I want to tell you about interesting part of the game theory, which usually not very common, because cooperative games is like not the main line, it's like side part of game theory. So nobody actually in short lecture courses, you almost never heard about cooperative games, so heard very little. But yeah, okay. So what is cooperative game? So non-cooperative game, as we considered before, it means that players. It doesn't mean that players do not cooperate. They sometimes cooperate, but this cooperation should be from the structure of the game, because player cannot just make an agreement and hope that this agreement would be binding, because they have no force when it comes to the choosing the strategy. So in non-cooperative games, it is supposed that when players make decision, they do it alone. They don't have any force that force him to make this or this decision. In cooperative games, it is assumed that there is a possibility to make a contract or some bindings that would be always well supported by some outer force. So what I mean? Let's consider the example. So 3 children, they want to buy as many candies as possible, and there are 3 options. You can buy a package of 500 grams, 750 grams, and 1 kilo. And these packages of candies, they cost $7, $9, and $11. Okay, and children have in their pockets, each child has $6, $4, and $3. So no child can actually buy a package by himself. Okay, so they need to cooperate, and they need to make some negotiation how to divide, how to buy as many candies as possible, and how to divide. Well, what is cooperative game theory proposing? Well, the main idea is that we can form coalition, and each coalition should be described or characterized by value function. So what is value function here? Value function is a value of coalition. So it shows how many candies this coalition can afford, can buy at maximum. So we have this formula. Well, usually the empty set is always 0, but here coalitions that consist of 1 member, 1 player, nobody can buy candies by itself, so it's 0 also. And first and second player, they can afford this. First and third, they can afford this maximum, and second and third, they can afford this 500. And all 3 can buy 1 kilo. So how do you think? Maybe you can propose some divisions which is like looks fair to you. The problem is fairness, that you can define different types of fairness, and in game theory there are a couple of notions, but let's not start with the fairness. So suppose that how do you think, what proposition is reasonable to you? How many candies should get first, second, and third player? If the rules like this, they have 6, 4, and 3, and the packages cost 7, 9, and 11. Oh, now I'll be in 5 seconds. Okay, any ideas? Okay, so the idea behind this division is that payoff of every player in coalition can be less than individual payoff, and payoff of every sub coalition and coalition can't be less than sub-coalition value, because otherwise, if you receive less payoff in big coalition, then it's better for you to divide and get better payoff by yourself. So if we consider this equation, then we find that if x1 is the number of candidates that get first players, x2 number of candidates that get second, and x3 is number of candidates that get third player, then sum of first and second should be bigger than 750, because they can do 750 alone, first and second, and first and third also, but second and third, they less valuable because they have less money, so they can afford at some only 500. So if we solve this equation, we will get unique solution, and this is a first player should get 500 because he get bigger amount of money, and second and third should have 250. So this concept is called core. So core is a concept to solve cooperative game by defining value function that describes the value of coalition. Another example, it's actually quite interesting. Many game theory examples, they have like some beautiful beautiful representation or images. So imagine a gloves economy. A gloves economy is first player has left glove only, and second and third have right glove each, but only one. And the cost of pair is $1, but glove without pair is zero. No value at all. So how to formalize this a game? They need to form a coalition, just to get this value. So here we have these numbers, and when we try to solve, we get some surprising results that first player should get all $1 by himself, because he is unique in this economy, and his unique skills, he can propose second or third to make a coalition with one or two and reduce the cost basically to the zero. So it's like limit result, of course, but maybe not very practical. But the idea behind this is that if you want to be if you want to have high salary or higher share, you need to have some unique skill or unique property. So no one else has. So this is like glove economy. If you have one right glove, then one left glove, then you can dictate your conditions. Okay, so now I want to tell you about another concept of cooperative game, which I think it's useful, can be useful for you also. And this is a fair pie division. So pie is actually a term from game theory. So suppose that we have two players, A and B, and player A can alone make one piece. Or, well, you can imagine this as a you can imagine this as a production of some product, and player A can create one share, and player B can create two. But together, if they combine their services, they can produce 9. So how they should divide this 9 between them? Well, they can propose, for example, equal division, or they can propose proportional division. But the problem with equal and proportional division is that they have a problem. For example, suppose that player 2, for example, player B, can make alone not 2, but 5 shares. And if they propose equal proposition that in cooperation, he will get less share than he can produce alone. So it's like pointless for him to form a coalition. So the division must include what persons do alone. This is why it's not easy. And if you think about proportional allocations, then it's also, yeah, I can produce an example where proportional allocation is not. Okay. So the idea of pi is the definition is following: pi is a summary payoff from cooperation minus sum of individual payoffs of players without agreement. So what is the pi again? It's a summary payoff from cooperation minus what players can do alone. So if pi is bigger than 0, then this is a reason why two players form a coalition to produce extra product. So, for example, here we have 9 in total what they can produce, but we need to remove first 1 share that player A producing and 2 shares that player B can produce alone. And we get 6, and 6 is a pi here. So pi here in this example is a 6. And if suppose there are only 2 players and they are needed for each other, so they can produce this, make this joint adventure, this joint production alone, they need each other for this, then it's reasonable to divide pi equally. Okay. So we need to divide pi equally, and then first player will get 4 shares and second player will get 5 shares. And this is division according to pi to fair pi division. It's called the principle of division. And this is actually very old. I mean, it was formulated maybe in game theory, but the science of this idea is actually quite old. There is a part in Babylonian Talmud that says about property with uncertain rights. So the book is say the following. So there are 2 people, 2 persons, and they found some clause, but it's actually can be applied for any property with uncertain rights. So, and one says this clause is mine, and the other says that this clause is mine. And if they and in this situation, the Talmud proposed to divide it equally. But there is a second part of this chapter, and if one says that it is mine and other says that half of this mine, then the Talmud proposed division 3/4 and 1/4, a quarter and 3/4. Why? Well, let's try to apply the idea of pi. We have a clause here. It's like 1 unit. And first player says that all this unit is mine. For example, I was first who found it on the street or road. And second player says, no, we do this at the same time. So as we found this clause at the same time, so I pretend on the half of this Well, probably if you see this problem first time, you have like an idea. Okay, first player wants 2 shares, second player wants 1 share. So let's divide proportionally. First player will get 2/3 shares, and second player will get 1/3. So it's like fair division, but it's not the case here. So what is Talmud proposing? That consider this clause as a one unit, and we have first player who pretends on all this, and second player who pretends only on half of this. So the contested part is only half of this part, because this this part already considered by second player to first player. So they need to divide equally only this part. And if we divide equally this part alone, then we have this recommended by Talmud, 3/4 and 1/4. But of course, all this is not written in Talmud. It's like a game theoretical principle applied to this strategic situation. And this idea allows you to solve a quite complex problem. I just want to, well, state this problem. I think I will not solve it to the end, but I just give you idea. So two companies, and they agree to develop some product, and the cost of this product is not known before, so the only range, some range, and but profits are expected to be proportional to the size of the company. So they do this product for themselves. And for simplicity, we assume that A expected profit is 100, and B expected profit is 200. So when we have costs 50 or 150 or 250, we need to divide this cost between companies. And the idea of pi allows you to do this quite easily. Okay. So, but well, what do you need to do? You need to calculate pi for each situation, and then form the divide pi equally and form the payoff of each player. But yeah, I think that you can try to do this by yourself, because not much time. So I want also to finish with the cooperative game. So let's go further. Lloyd Shapley is very prominent scientist of cooperative game theory, and he got Nobel Prize in Economy with Alvin Roth, as I already said. And he was author of idea of another division principle, and this principle called Shapley value. And actually, it's very useful, especially if you need to calculate some allocation automatically between quite big amount of players, and it's very good for programming. So let's consider what is Shapley value on example. We have three companies, and they want to build airport, and they need to this line for planes. So, and first company needs length 1, and second needs length 2, and third needs length 3, and each part costs 100. How to divide costs between these three companies? Well, let's put pi division graphically, for example. So we have three. If they implement it separately, then company A will play 100, company B will play 200s, and company 3 play 300s. Okay, but if they implement this together, then you see that first part is used equally by three companies. So they just need to divide the price on 3. Yeah, 3 and 1/3 for each. And this part is used only by B and C company, so they need to divide it for 2 players equally. And this part is used only by C, so C must pay full price for this. So in this way, so C must pay this amount, B must pay this amount, and A must pay this amount. And this is a graphical solution, but in more complicated game, you can't actually draw this. So the idea of Shapley is to make some combinatorial calculation where you have, you need to write down all permutation of players, and then you write down the value that this player brings to the coalition. So, for example, here we have A, B, C ordering, and so comes A, he builds the rod that he needs and pays 100. Then comes B, he pays the part of rod that he needs and pays 100. Then came C and pays the part of rod that he needs, so it's another 100. Then ACB, A came in and built the rod that he needs. Then C came and built rod that he needs, 200. And B came and there's nothing for him to build because it's already built by C. And we do this for every possible permutation, and then we calculate the average. And for the average values, we have the same numbers as we get in graphical representation, and this is a Shapley value. Another useful example of Shapley value is, for example, we have a taxi and we want to allocate cost because three friends of 3 players, they order the taxi and they need first player, for example, need to ride for $20 and second for $80 and third is for $120. And if they ride together, they pay only $120. And there is $100 extra. This extra is actually the pie that is created by their cooperation. So they need to split it, and they can't just split it equally because this way they just need to pay A more than 20, and it's like not realistic at all. And Shapley value is very useful for such situation. We need to create this table with permutations and calculate the values. So you can think about it that well, first player need to pay 666, second 3666, and so, and it's actually I've heard about real applications that algorithms that calculates the allocation costs for different players that form a coalition for something. So Shapley value is really useful things. Okay, so, and I think last part that I want to tell about is the matchings, and this is like quite a hot topic because it's last Nobel Prize, and the idea is that in it's a long story, but it's really useful for kidney matching and for college admission system matching and for many other matchings also, especially in education where you have, for example, you have students and you have professors, and these professors give some term projects, and each student like create a rating of these projects, and then you need to match students and projects in best possible way automatically, so that each student gets the best possible matching in this situation. In 1962, David Gale and Lloyd Shapley, they published a paper with the exciting title "College Admission and the Stability of Marriage." Okay, and what was this about? What is this? What's the matching, bipartite matching here? So we have two sides, like for example, let's say small a, b, c would be I don't know, males, and A big, B big, C big will be women, and they have some preferences on the set, and we want to propose a matching. It's actually original paper. It's marriage problem, called marriage problem, but they use it for also for student high school, college education matching. But for simplicity, let's consider that we have three pairs, and it's not actually easy to produce a good matching if you have many different participants. So, for example, we can propose first matching that we can imagine. It's A, B, B, C, C, and this matching is not stable. What is stable in game theory term? Well, it's actually close to the notion of equilibrium. You know, if you remember that equilibrium is a point of profile of the game that nobody wants to deviate. And here matching is stable if there is no pair who wants to deviate and form another pair is better matching. So here, if we produce index, we produce index for each participant. Index is their choice of in their preferences. So we have that here BC can form a better match because index of a pair B big C small is 2, 1, and it's an improvement for B, and this is improvement for C. So this matching is not stable. So let's deviate, okay? And then we have also, we don't have stable matching because pair NB has a better improvement index. And sorry, my laptop is out of power, so I need to switch on battery. Switch on. Okay, so here it's also not stable matching, and finally this only for fourth step is a good matching. And this is a problem if you have a big, quite a big amount of participants. How to create a big good matching, and is it really the case that this good matching is existed? Maybe there's no good matching at all. Maybe there's no stable matching possible. And Gale and Shapley answered these questions positively. So stable matching always existed. It's you can find it by using algorithm of Gale Shapley. It's also deterrence acceptance algorithm called, and you can, but the stable matching is not unique. Yeah, so it's different stable matchings, and this algorithm prefer one side. If you have this algorithm, then the one side will always get better matching possible, best possible matching. So this is the idea of matchings, and there is also top trading cycle matching, quite famous algorithm. And my point is that game theory is also using for producing matchings and for testing these matchings on stability. So how player can manipulate this matching system, and is it possible to produce better matching by cheating with your preferences? Is a problem of game theory. Okay. And now I think the last topic is about voting systems, because I want to show that game theory is also using for different voting systems, and I think I will finish on this. So what is a voting system by point of view of game theory? Well, we have some participants, some voters, and each voter has a set of preferences. So, for example, first voter wants tea on first place, and then coffee, and then juice. And second voter wants coffee at first place, and then tea, and then juice. And third wants tea on first place, and then juice and coffee, and so on. So we have an amount of voters, and each voter has these preferences. And function, oh, sorry, I forgot to, system of social choice is a special function that translates these preferences to the one vector with decisions, where first number of this vector is the most preferable choice by society, by voting system. Second is the second, and third, and so on, so on. So it's very important, for example, if you have some social projects and you want to give money for some social projects, but you don't know what are best projects. So you ask people, what do you want to implement for some common money, for some budget? So people try to put their preferences that I want this project in first place and this on second and this on third, and then we can put together all this, aggregate all these preferences and produce some list of projects. So this is a system of social choice. And what we want from this system? Well, first obvious is we want that this system can define a winner, okay? And this system should express voter preferences as good as possible, and also be good in the sense that shouldn't produce some paradoxes and be stable to manipulations. And one of the, well, it's not exactly game theory, but Kenneth Arrow, he got Nobel Prize by economy, but he also produced a theorem of impossibility, or Arrow impossibility theorem. And by this theorem, he said that under some assumptions that we actually expect from voting system, it's not possible. Oh, okay, exactly. He says that if we have a system that always produces a winner, has two properties of longevity and irrelevance of and two quite natural properties, then the only system that is satisfied all this is a dictatorship. And if we add no dictatorship, then no function is possible. So the consequence is that actually any system that we have has some paradoxes or problems, any voting system, and we have many of them right now. But I think there is the best one. It is used in electronic voting and so on. It's called Schulze system of Schulze system. Okay, I just give you a couple of examples of manipulation of our different of our usual system. So, for example, we have single voting plurality without any second tour. So it's just who gets plurality of votes, then he won. Who gets the bigger amount of votes is the winner. So, for example, we have 180 voters that have these preferences, 170 that have these preferences, and 40 that have these preferences. And if they came to the day of election day to this system, yeah, and they vote, and right now the Tomcat is the winner. He gets the most number of votes. But now we want to manipulate this. We produce a sociology, and it's actually correct, absolutely correct, of how will, for example, 10% of all voters, how they will vote. And this is published in some papers that 36 prefer this one, Tomcat, and 44 prefer Bugs Bunny, and only 10% prefer Winnie the Pooh. So as a result, 30 voters from the last column, they switch from the first choice, which has no chances at all, to the second chance, and now Bugs Bunny is the winner. So producing this sociology influence the result of the election. Another interesting paradox, it's a paradox of second-hand winner. Suppose we have 3 professors were tired, and they at Friday they want to go and drink something together, and they have a little time, so they agreed to vote by pairs and eliminate one member of this pair who gets less amount of votes. It's actually a system in which is in act now in Congress when you in Congress, in American Congress, when you vote for the bills, for the law, then you have this system. You have a pairing, and then the winner go to the next pair. So, for example, first they vote what is better, wine or rum, and you see that rum. Second professor thinks that rum is better, and third professor thinks that rum is better than wine, so they remove wine. Then they vote rum against beer, and third professor thinks that beer is better, and first also thinks that beer is better. So then they vote beer against cognac, yeah, and they think that cognac is better than beer, and this also thinks that cognac is better. So two wants cognac better than beer. So they go to drink cognac, but all three professors actually thinks that wine is better than cognac. All three of them think that wine is better than cognac, but this procedure produces cognac as a winner of their voting. So this example how irrational can be choice of system of society and contradictory to intuition about the single preferences. Okay, so that's it. I think that I I make you tired. Okay, so thank you for attention. And if you have any questions, please write them. I can consider. Well, the problem, okay, about proportional division of pi. The problem with proportional division of pi is that if you have players that like huge players or big players and small players, the proportional division will discriminate small players a lot. So, for example, you need, well, for example, you have like production of for example, 5 points, and other can produce themselves 1 point, but together you can produce like, I don't know, 15 or 20, and you need each other equally, but if you make proportional, then the first player will get lion's share, almost everything. So proportional division is not good if you, well, you can construct situation where proportional division is not obviously not fair. I think that I can, maybe in this situation it's not looks like too unfair, but I can construct it that it's not the Ukrainian election system is not the game theory problem at all. It's about other things. So yeah, at least we should start to how to get election system better. Do not change it at least for 20 years, so people can adjust how it works. Because if you change the election system every election cycle, it's not good. It's good as not good. This is not good. But it's an irresistible temptation. If you a leading party, you want to, the first thing you want is to change the election system. Okay, I just check the question in Slack and in YouTube. Okay, I promised some sources about game theory, but I didn't actually prepare them, so I will try to do this today in putting them in Slack as like some list. Yeah. Okay. So yeah, there are a lot of books. Kidney matching. Well, okay, about kidney matching is Alvin Roth. It's I surely recommend the like first hand source about them. It's a book of Alvin Roth called "Who Gets What and Why." I think he wrote this book after he got Nobel Prize. I can show you the book. Uh, So this is a book, Who Gets What and Why. And this is about matching problem and how Alvin Roth, how he applies this idea of matching to the school matching in, I believe, in Boston and New York. And then how he applies this to the kidney exchange problem and how they became successful, very successful actually, very successful algorithm. Yeah, about, well, game theory actually not about, yeah, actually there is a movie which is deeply based on game theory, and I have a lecture, a scientific popular lecture about game theory in movies. I if you're in Ukraine, you can check my Facebook. Maybe I will repeat it. I did it, I think, 2 or 3 times. And Dark Knight, Christopher Nolan Dark Knight is actually about Joker and Batman. Is actually a movie that is deeply based on game theory, because every situation is strategic situation, and Joker is like a game theorist that constantly constructing some interesting situation. Okay, so it's about, and yeah, you have movies about Alan Turing and about John Nash, A Beautiful Mind, about life of John Nash. It's not exactly about game theory, but it's a really nice film movie with Russell Crowe as the main as Nash. So you can saw this, of course. About books and courses, well, about list of books I will write in Slack, and about courses, if you use Coursera, there are two very good, I think, a couple of courses I can recommend. First of all, it's Stanford course, Game Theory 1 and Game Theory 2. Two courses. It's like a very nice introduction into game theory. And second one is a Jerry Nailbaugh course, Art of Negotiation, and this is also about game theory, and very interesting course. Okay, how to use game theory, especially Nash equilibrium, and machine learning and reinforcement learning. Well, basically, as far as I understand it, when you use reinforcement learning, you use game theory um, to understand, well, to check or to prove that equilibrium exists, that equilibrium is here. So when you have a theoretical framework that should be in equilibrium, then you can start to launch algorithms to found it. So yeah, it's actually, I think it's heavily dependent of the area of application, and when you have some game, for example, you know that you have theoretically you have some equilibrium predicted, and then you can start to construct algorithm and check how to check are these algorithms are working towards this equilibrium or not. So game theory basically provides a theoretical checkup for the almost heuristic algorithm. So when you have some problem of game theory, you can create an algorithm, you can launch, found solution, and then compare with the theoretical solution, and make some suggestion how to improve the algorithm if it's not converged to the theoretical solution. So it's like I think mainly checking tool and also prediction of how algorithm will behave in general situations. Okay. Any application of game theory in day-to-day life that you would recommend to implement? Well, it depends of your life, but I thought about, I told about this art of negotiation course in game theory. I surely recommend everyone because it's like how to use game theory in everyday transaction when you communicate with other people. So it's very useful for your everyday, I think, life. So art of negotiation, Coursera, Barry Nailbaum. Okay, can you suggest any work that combine game theory with neuroscientific studies and cognitive psychology? Colin Kammerer, he actually the father probably of behavioral game theory or experimental game theory, how it's called. He wrote a book about neuronomics, and I think he's the one leading authority of combining game theory and neuroscientific science studies and cognitive psychology. So you can, I think, address his book about and maybe some references from his book. So that's a Colin Kammerer. I just show you. Yeah, so yeah, here behavioral game theory, experimental strategic interaction, advances in behavioral economics, neuronomics. No, I think okay, and I forgot the. But yeah, I think you can start from this. Yeah, Colin Cameron. Okay. Any other? If you Ukrainian speaking participant, I can also recommend my blog about game theory. It's like scientific popular papers. So you can, if you can read in Ukrainian, then you can find this. Yeah, it's site you are, and then Olexii Ignatenko, and here's some articles about game theory. So if you're interested in some parts, you can read here. Okay. If there is any no question, but if you have any question, you can write me in Slack, and I will answer. So yeah, see you.